Okay, and welcome to another video. This time looking at an energy question for technological studies, and we've got a situation here with a ball that sits on top of a static shelf. So at its maximum height it's got full potential energy, but we know later on that it's going to fall from the shelf and it's going to eventually hit the floor. So we've got position A and position B. Position A has got maximum potential and position B has got maximum velocity. Okay, let's see what we can do with this question. First part is calculate, showing all working units, the potential energy of the ball. Well, we know that we've got a mass, and that is 0.7 kilograms, and we know that we've got a height, and that is 10 meters. We're asked to find the potential energy, so the first thing we write down is the formula. Energy potential is equal to mgh. Now g here is a constant and it's gravity, and that is equal to 9.81. So the first thing we put in is the mass, 0.7 kilograms. Then we put in gravity, 9.81, and then finally we put in the height, 10 meters. Now it's time to get the calculator out. 0.7 times 9.81 times 10 equals, and my answer 68.667, and the units of energy joules. Okay, so that's my maximum potential energy. Next part of the question, it says assume that EP is converted into EK, so it even gives you that the potential energy is converted into kinetic energy. So when we looked at the original picture, we saw maximum potential energy, maximum kinetic energy, zero potential energy, zero kinetic energy. So let's have a look at converting these. We know that the formula for kinetic energy is energy kinetic is equal to half the mass times the velocity squared. We know the energy kinetic is equal to energy potential, so 68.67 joules is equal to half the mass, which we know to be 0.7 kilograms, times, in this case the unknown is the velocity squared. Okay, so I've got the formula. I've got to find now velocity on its own, so I've got to transpose the formula, and the way that we do this is we take half the mass over to the opposite side, and because it's multiplied on this side it's going to be divided on that side. Way of showing that is divide both sides by the same amount, half the mass, half the mass, and these two of course cancel each other out. So we're left with 68.67 divided by half of the mass is equal to velocity squared. Let's do a little calculation on that now. 68.67 divided by 0.35 equals, and I get an answer of 196.2. But that is equal to the velocity squared. Now if we want to find velocity on its own, we need to take the square root of 196. So we cancel the square, we put 196 square root, and on the calculator that works out at 14.007. You can forget about the 077. It's not necessary. The units for this, velocity, is meters per second. Okay. Moving on to the next part of the question. It says, when the ball bounces, it does not reach its original height, so some energy is lost. Well, when rubber contracts and expands again, if it does it several times, you'll actually notice an increase in temperature. So one of the energy forms that's lost is heat. And if it's in a very quiet room, you'll be able to hear the ball bounce, so the energy from producing the sound has to come from somewhere, and it comes from the ball. So that's sound. Moving over the page, we've got renewable energy now. It can be generated from a number of different sources. State 1 disadvantages for using both these types. So tidal energy, if you know, is when the sea rises and falls again. However, it does it about once every 6.5 hours, but there's 2 times when it doesn't actually rise or fall, and that's at peak high tide and peak low tide. So we can say that at high and low tides there is no movement of water. And the next is wave energy. Well, the wave is dependent entirely on the weather, so at some times there are simply no waves due to the weather. And that is the end of the energy question for today.